Hello everyone, my name is Shovik Munglik. I am Assistant Professor of Electrical Engineering Department of Holi Institute of Technology. Today I am going to explain the topic stationary pulsating magnetic field in single phase induction. So according to Oersted law, whenever there is an electric current, there will be magnetic field. So if we give a constant current like DC, the magnetic field that will be created will be a constant magnetic field. In three-phase induction motor, when a balanced three-phase supply is given, a rotating magnetic field is produced. In the same way, we are going to find out that in single-phase induction motor, what kind of magnetic field will be produced. So in single phase induction motor, there is only one phase. So single phase AC supply is given. That single phase AC supply is shown over here. As you can see, there is a sinusoidal current which is varying sinusoidal with respect to time. So this total sinusoidal waveform are divided into some instants are taken. That is, at instant 1 current is 0, at instant 2 current is positive but not maximum, it is some intermediate positive. Similarly, at instant 3 the current is maximum positive, at instant 4 current is again intermediate positive, like this. Instant 5 current is again 0, in 6 current becomes negative, intermediate negative. At instant 7 current is maximum negative, at instant 8 current is again intermediate negative, and at instant 9 current is again 0. So this is a full cycle. After this the current will repeat itself. So this kind of single phase supply will be given in the stator winding of single phase induction motor. Now, the stator of a single phase induction motor is drawn here. So, to represent each instant, as I have discussed, 1 to 9, there are total, so individually, the 5 stator waveforms are drawn. I will explain them one by one. First, this one, as it can be seen, that this is the stator construction. Now, A dash is the single phase AC supply. Single phase AC winding. That means here we are going to give single phase AC supply. So, as we can see, there are three conductor positions are taken. What is actually meaning of this? So, a coil has two coil sides. A dash is a three-turn coil. So, three coil side in this side, three other coil side in the another side. So, it is wound like this from starting from here A dash, A dash, A dash, dash. So, this is a three-turn coil. Three-turn single phase coil where we are giving a single phase AC supply. Now, let us start with instant 1. At instant 1, as we can see, the current is 0. So, if there is no current, so there will not be any magnetic field created. Now, let us come to instant 2. At instant 2, current is positive, intermediate positive. Say, when the current is positive, A coil sides will be dot. So, if one coil side is dot, the another coil side will be cross, because dot means current is coming out and cross means current is going in. So, if current comes out from here, it has to go in from the A dash coil side. So, at instant 2, when the current is positive, say A coil sides are positive, so obviously the other coil sides has to be that means cross, that means inward. Dot means outward, cross means inward. So, what will be the magnetic field for this kind of current? We have to use right hand thumb rule. dot outward, so current is coming outward, that is the direction of thumb, and the other fingers will show me the direction of magnetic field, that is upward. From A dash also we can verify that current is inward, so inward current, the magnetic field is in the upward direction. So here magnetic field upward, but as the current is not maximum positive, intermediate positive, so the upward magnetic field also will be some intermediate upward magnitude. On the other hand, let us come to instant 3. At instant 3, the direction of current is same as instant 2, because here at instant 2 current is positive, at instant 3 also current is positive. The only difference is at instant 2 the magnitude of current is small, at instant 3 the magnitude of current is maximum. So that means here also the dot and cross position will be same as this one. That means positive current we have taken A as dot, negative current we have taken A dash as cross. So current is coming out from here and going in through the A dash coil side. Now at this point, as this current is maximum, so the direction of magnetic field will remain same as this one, but the magnitude of that magnetic field will be larger. So it is shown by a larger arrow. The direction of magnetic field is same, but the magnitude will be larger. Now let us come to instant 4. Now at instant 4, as you can see, as instant 4 and instant 2 has the same value of current, positive current, intermediate value. So it can be represented by this instant 2 and 4 will be same. One thing to notice here, that the direction of current is same and the magnitude of the magnetic field will be reduced as compared to 3. Now let us come to instant 5. Current is 0. So if the current is 0, again this condition, 0 current, no current, that means no magnetic field. Now let us come to instant 6. At instant 6, current is negative, but not maximum negative, with some intermediate value. So here the direction of current will be changed. That means now A will be crossed. Ideal for 2, 3, 4, 2, 3, 4. In these instant, A coil side was dot, A dash coil side were cross. In this case, as the direction of current has changed, so earlier if the current was coming out and going in like this, now current has to, direction of current is changed, so now current has to come out from here and go in through the A coil sides. So A coil sides will be cross, A dash coil sides will be dot. Now as you can see that we will apply right hand thumb rule. The thumb will point toward the direction of current, inward current, and the magnetic field will be downward. Here the current will be outward, again the magnetic field is downward. So now the magnetic field will be downward. The magnitude of the magnetic field, downward magnetic field, will be some intermediate value. Now let us come to instant 7, where direction of current is same as this one, but here the value of current is more. So the value of downward, magnitude of downward magnetic field will be more. Now let us come to instant 8, same as this one. 6 and 8 has same value, so this one has the same value. Instant 9, current is 0, so this one, no current, no magnetic field. So one thing we can notice from this is that if I see the nature of the magnetic field, initially it is 0, then at the same position it is some intermediate upward position. Then at the same position it is maximum, then again it comes to intermediate positive, then comes to 0, then negative, then maximum negative, then intermediate negative, then again 0. So if I start from this position 1, at 1 it is 0, at 2 in the same position intermediate positive, 3 at same position maximum, again 4 intermediate value, 5 again 0, 6 negative, 7 maximum negative, 8 again some intermediate negative, 9 is 0. So that means at same position current is pulsate, current is varying sinusoidally, the magnetic field is pulsating in nature. 0 intermediate positive, maximum positive, again intermediate positive, 0 negative, maximum negative, again intermediate negative, 0. So at same position the magnetic field is fluctuating or pulsating or oscillating in nature. So that is why it is called stationary pulsating magnetic field. Now this stationary pulsating magnetic field MMF can be represented by some equation. Before going to the equation, one thing we will see from here, that what is the axis of the winding? Around the axis where we wound, that is called axis of the winding. That means in this case, along this horizon, along this vertical line, we will wound the axis. Along this vertical line, we will wound the axis. So this will be the axis of the winding. Around this vertical line will wound the winding. So this vertical line will be the axis of the winding. In the same way, if we do the winding here, the winding is done like this. That same A dash coil or A dash coil is given here. The position is changed. Earlier the position was here. Now the position just rotated by 90 degree. Now the position is here. To represent that both are same. Now here the axis of the winding has just changed. Around this horizontal line the winding is done. This is only the difference. Now you see, so along this horizontal line that winding is done, A dash winding is done. Say at any instant this side is dot, this side is cross. These conductors are cross, these conductors are coil sides are dot. So what will be the direction of magnetic field? So thumb represent the direction of current, magnetic field will be in this direction. Similarly, thumb represent the inward current. So this will be the direction of magnetic field. So the magnetic field is shown. What is here? This black ring-like structure is the stator, and inside the stator this blue structure is the rotor. So as you can see, the flux are coming out from this, from the stator from here, and it will go in through here. So this portion is the north pole, this portion is the south pole. Flux is going out from the north pole and coming in through the south pole, as we can see through here. So north pole to south pole. Now the same thing if we flatten, that means suppose this ring is cut and it is flattened. So what will happen? So this black ring, if it is flattened, this will be this black line, and the rotor blue color circle if or ring, if it is cut and flattened, it will look like this. So same thing, instead of circular, if it is flattened, then it will look like this. Now if we start from this conductors, that is in cross. So cross, suppose we are rotating in this ring, so cross, then comes north pole, then comes dot, then south pole, again back to cross. So similarly here, as we rotate, if we have to see the same thing here, we have to move in the straight direction. That means start from the cross, here we are rotating, here we are, this is rotational motion, this is translating motion. So here we are rotating, here we are going forward. So from cross towards, if we move, we will face north pole. Then if we move, we'll see the dot conductors. Then we'll move, we'll see the south pole. Then if we move, we'll face the again cross conductors. So here cross conductors are shown twice to represent that we have started from cross, we have gone through the full circle, again we have reached at the cross position. We have started from cross, we are going forward, so cross, north, dot, south, again we will come to the cross position. So same kind of magnetic field, cross inward current, magnetic field downward, outward current, magnetic field downward, inward current, magnetic field here upward, here upward. So if, as you can see, the magnetic field is going in through to the, sorry, the magnetic field is coming out of the stator pole, so north pole. Here it is going into the stator, so it is south pole. Now, as we can see, in the axial region, axis of the winding, the flux is maximum. This is the axis of the winding. Around this axis, the conductors are wound. So, in the axis of the winding, maximum flux are there, but near the conductors, there are no flux that is coming in or going out. There are no flux. So around the axis of the conductors, there are maximum flux. So to represent that, in the axis of the conductor, the flux is maximum, and at the position of the conductors, the value of flux is 0. Again at the axis it is maximum, and here again it is 0. So if we start from the axis of the conductor to rotate, if we start from this position, so if we start to rotate from the axis of the winding, that means we have to start to move from this position. If we start to rotate from here, what will happen? Alpha is, so from where we are starting, that is called alpha. From here, if we rotate, we'll get the dot conductors. Then if we rotate, we'll get the south pole. Then if we rotate, we'll get the cross conductors. So at alpha equals to 0, that means at the axis of the winding, maximum flux are coming, the value is maximum. When we rotate 90 degree and come to dot, that is alpha equals to 90 degree, the value of flux will be 0. If we rotate another 90 degree, that is 180 degree total, so at this position it is maximum negative. So this curve, if we start from alpha equals to 0, this curve is following a co-sinusoidal waveform, which is maximum at 0, 0 at 90 degree, maximum negative at 180 degree, again 0 at 270 degree, like this. So this curve follows a co-sinusoidal pattern. Now what is the name of this angle alpha? Alpha is called space angle because we are rotating in space. From the axis of the winding. This is the axis of the winding around which the conductors are wound. From this axis of the winding, if we rotate, then that means from this alpha equals to 0, we are moving forward. So this angle alpha is called space angle. That means we are rotating in space. So if we have to represent the MMF, magnetomotive force, how we can represent that stationary pulsating MMF? How we are going to represent that? The stationary, in the previous slide we have seen that according to the sinusoidal current, the magnetic field is, the magnitude of magnetic field is changing sinusoidally. So there will be one sinusoidal term with respect to time. That means what? The magnitude of the MMF is varying sinusoidally like current. So this F Sm sin omega t, this is varying sinusoidally. This represents the magnitude of the MMF. And what is cos alpha? Cos alpha is the distribution of the MMF in space. How in space this stationary pulsating MMF is distributed? As we can see that in space, if we rotate it, the from the what is taken alpha equals to 0? Alpha equals to 0 is at the axis of the winding. So from the axis of the winding, if we rotate, it follows a cosinusoidal graph. So that's why cos alpha magnitude is varying sinusoidally, distributed in space as a function of cos. So total MMF wave is represented by F equals to Fm maximum MMF Fm sin omega t, that is magnitude is varying sinusoidally, cos alpha, that is the MMF is distributed in space as a function of cos. So this is all about the stationary pulsating magnetic field, and this is the equation of the stationary pulsating MMF wave. Thank you.